So let me just,
Okay.
I'll have to make you a host and then you're able to share your screen. But for the people that are on the call who haven't met Andrew, so Andrew is a postdoc at the Brigham and Women's Hospital and Harvard Medical School, and he recently received his PhD in 2020 from Weill Cornell and the Tri-Institutional Training Program in Computational Biology and Medicine. And his research interests include molecular drivers of cancer, the diagnostic process of pathologists working at the microscope, and crowdsourced pathologist opinions on social media. So I actually came across some of your work on Twitter, Andrew. That's the first place that I saw your work, and I thought it was really fascinating on how you combine deep learning and computational pathology and social media. So I think we're in for a treat today, and we're really looking forward to your talk. So whenever you're ready, it's an honor to have you again today.
Well, thanks very much, Simon, for your introduction. I wanted to be part of the speaker series. I'm honored really to be here. So let me, with that, share my screen if I can, and we'll get started then. So is everyone able to see my screen?
Yeah, that's perfect.
Okay, so, right. So the title of my talk is Computational Path from Microscope to Social Media. I'm Andrew at the Brigham, and from time to time, you'll see these little QR codes. I just include that as a convenience. I understand this will be on YouTube, so feel free to scan those with your smartphone and get taken to the corresponding literature, or in this case, Faisal, lab website. I'm delighted to be a part of his laboratory. So with that, there are three main parts of this talk. There's an underlying question. Hello, is there a question on? Okay, there's three main parts to this talk. And the underlying question is, what is important in the slide? And I'll start out with a pretty small pilot study called Deep Scope, where we video recorded pathologists at the microscope making a diagnosis. The second project I'll talk about is Pathobot, which Simon referred to on social media in a way. We collect photomicrographs from pathologists on social media, and so they tell us directly what's important in a slide. It is those, photomicrographs. And then finally, I'll wrap up with a project that's personally meaningful to me, Pathobox. It's a 3D printed mount to put smartphones on microscopes and encourage more sharing on social media. And it's a good training tool. So let's get started. So this is our first pilot study. It was very early work in my PhD. We called it Deep Scope. I'm grateful to my collaborators, Dr. Sergikun, Hikmet Al-Amadi, Peter Schiffler, and Thomas Fuchs. There again is a QR code if you'd like to go directly to the PubMed article. You're welcome to do that. The next slide shows a surgery, so a little bit of a trigger warning there. If you're sensitive, you may want to look away for a slide. I see something in the chat. Yes.
Yeah, so that was just me saying, please ask any questions in the chat for people who are online. So you can just ignore that one for now, Andrew.
Great, thanks. So let's get started. Bearing in mind there's a picture of the surgery next. So I include this just because it depicts what happens. There's a surgery at the upper left. In the upper right, there's some excised tissue. That tissue is cut up into slices, and in the lower right, sections are formed, so we can see the nuclei and stromal tissue here. And the pathologist uses a microscope to look at that slice or look at that tissue and diagnose what's wrong with the patient. So we thought we would video record that process in a way. And we were motivated to do that because at the time I was at Memorial Sloan Kettering Cancer Center here in New York. And they're producing about 1 million slides each year. So that's a lot of slides. So we thought if we had a way of measuring and predicting diagnostic saliency in these slides, we could separate the signal from the noise, so to speak, and scale up for other machine learning tasks and focus on regions of interest. And so what we endeavored to do is make these heat maps. So you see a heat map we made, and that's the time in seconds that the pathologist spends in different regions of the whole slide. And red hot regions just have aggregated more time. And you see in some regions the pathologist looks, and in some regions the pathologist doesn't. So the question is, what is salient and looked at for some time, and what is not looked at or not salient? So those are our measurements. That's what we set out to do. So we are measuring saliency without changing clinical workflows. Presumably the clinical workflow is microscope based. There has been some changes in some institutions to be more digital. At the time we focused on a microscope. There's a lot of great literature on saliency with eye tracker studies and mouse tracker studies and viewport tracker studies like Merck in 2014. In the upper right here, you'll see some regions are white hot in heat and time. Those are looked at for a longer period of time by a pathologist. And that's something like what we're measuring, but we're measuring at the microscope and not at a graphical user interface or a computer monitor. So there's other great literature out there that expressed some concern or some potential confounds with using monitors and digital workflows, with potentially using peripheral vision. You don't have that at a microscope. Having the ability to turn your head, or having too much detail or different monitor resolutions. So there were questions in the literature about, maybe the digital workflows are fundamentally different in some way. It's good to ask questions, of course, but later on, there was literature the other way saying, based on the measurements they had, the whole slide imaging-based diagnostic process, a digital workflow, is actually diagnostically equivalent to a glass microscopy-based, microscope-based workflow. So it's not any different actually in their study, but it was a little bit slower digitally, about 20% slower in efficiency per case. So a very important study in our field there. And there are other kind of really important studies in our field about inferring where important regions of interest are. So Campanella et al. Was the first study to, at scale, use something called weakly supervised learning to infer where a tumor was from only a whole slide level annotation. Like we just know in the slide there's tumor somewhere, or there's not tumor anywhere. And so then machine learning can infer where that tumor might be. For our study, just a little bit earlier, we measured saliency at the microscope, directly video recording pathologists and aggregating time over those whole slides. Microscopes, of course, have been around for a long time and are ubiquitous in pathology departments. So something I'd like to show you is a 10x slowdown of the diagnostic process at the microscope. And you see a grid of green dots here. And from time to time, when the microscope field of view moves, you'll see some green lines out of those green dots, those movement vectors from global optical flow. And that's how we measure movement. So if the slide, if the field of view is not moving, there are no vectors here. And then we know to aggregate time. If the vectors are moving, indicating some movement, then we know that we should not be aggregating time. So that's just how we do movement detection. Of course, the pathologist moves quickly. They have a lot of cases to do in a day. So this is not slowed down, and it's quite fast. So our saliency pipeline is this. So we 3D printed some mounts. You can see it with the mount like this. We've come a long way since then, but we put this 3D printed mount on an eyepiece at a tandem microscope. And at the time we used a cheap, about $100 compact flash camera. And we measured, we video recorded the pathologist making a diagnosis. With those video frames, we had a 3-part sort of analysis pipeline there. So we could detect when the microscope's lens was changed for different power. We did motion detection also, like I showed you, and we did image registration using surf interest points and a ransack-based method. And that image registration is important so we can superimpose the time we measure from the camera over the whole slide image. So we have a glass slide that's run through a whole slide scanner that's patched in the usual way. And then those patches from the digital whole slide, we use image registration to find the correspondence between individual video frames for aggregating time and the tiles from the whole slide image. And we get something like a heat map And from that heat map, we can formulate a binary classification problem. So the neural network here is learning to predict from the whole slide image, which has time now. Is the pathologist looking for a long time or a short time at an individual tile in the whole slide image? Is there a long look or a short look here? Is it more than 1/10 of a second or not of dwell time? And so we can train a neural network to predict what regions in this sense are salient or not. So just to review the motion I'm showing here at the top, how we detect motion with global optical flow. And at the bottom, there's a visual artifact that we noticed when the objective lens is changed to higher or lower power. It changes the bounding box that is apparent to the camera that we have at the eyepiece. And that bounding box gets reduced. And that's just because the mechanical parts of the microscope will move the lenses slightly outward when you change those lenses. So that's how, oh, there's a raised hand here. I'm happy to take questions.
Yeah, that's just me, Andrew. So I was just going to ask, so you said that this is a binary task. How did you determine what your threshold would be to binarize the outcome?
That's a great question. It just happened to cut our data set approximately in half. And 1/10 of a second is a relatively short look, qualitatively speaking. So we want something that's approximately 0 seconds, maybe not exactly 0 seconds, and give us a nicely partitioned data set for machine learning.
Okay, and was the purpose to understand how the pathologist looks around the slide, or did you use this method to try and help understand where the important and diagnostic regions were?
We did. So I'm going to try to answer your question 2 different ways. So we predicted long regions versus long look regions versus short look regions. And we used that in subsequent work. I'm not actually talking about that particular work in this talk, but we wanted for predicting driver mutations in prostate cancer. It's a separate one with predicting is the SPOC gene mutated or not. And so to winnow down the amount of information in whole slides, we use the saliency predictor in part to leave us with only the salient tiles in the slides. So it can be part of a larger supervised or unsupervised learning framework.
Yeah, so because I guess the pathologist would dwell, as you like to say, for long in the more diagnostic areas. So I guess implicitly that's what the network would be learning, right? It would be learning the more diagnostic areas within the slide.
That's right. And the intuition for us there was if the pathologist isn't looking at it, it's probably not important. If the pathologist is looking at it for a long time, it might be important. It's not really that clear cut all the time. Like maybe the pathologist is looking at a region for some other reasons. Maybe it's an unusual region. Maybe it's not a region that's has a morphology that's so easy to recognize. Dwelling isn't necessary. So there are some questions like that. But we had to draw the line somewhere. So for us, empirically, the 1/10 of a second happened to partition our data set well and give us something that worked on a small scale, at least for this pilot study. But certainly this could be scaled to more slides and more institutions. And maybe we could partition things further, like very long looks versus not so long looks versus non-looks, or do something like regression. But binary classification is a relatively simple kind of task for us to learn as a starting point.
Okay, perfect. Thank you.
Okay. Sometimes I don't always fully answer questions, so I thank you for sticking with me there, working so we can get clarification.
No, perfect.
So we have some heuristics too about what registration is good. So you can imagine a video frame could register, it could overlap with a number of different tiles that we take from the whole slide. So these are 2 overlapping tiles at the bottom. And our question is, for this video frame that we have from the camera on the top, which one is the best registration? So if you think this top photo here, the middle of that corresponds over here, where this green line is at the end, we can measure the distance from that point on the green line to the center of the image patch from the whole slide. And that gives us a distance, like the off-center distance, how off-center the video frame is from the center of the patch from the whole slide image. And we want to minimize that distance. We want the greatest overlap for the most highly corresponding tile to the video frame. And so then on the right, we do this again for intuition. The center is a little bit off the patch, and that line is a little bit longer. So the distance is greater, so that's not as good of a registration. So ideally, the video frame center overlaps perfectly with the center of the tile from the whole slide image, but that's not always possible. So we try to make that overlap as close as possible. That makes sense. For deep learning, we're just talking about deep learning, we used the CAFE framework. This is CAFE-net. It's a lot like AlexNet. It was pre-trained at ImageNet, and we used that for binary classification, sending these whole slide image patches through to make the classification. Our pilot study was 4 slides, 2 tissues, and 2 pathologists, prostate adenocarcinoma and bladder cancer. You'll notice on the right, the prostate slides look relatively uniform, and they're thin strips of tissue. That's an artifact from the nature of the procedure, which is a needle biopsy, and the needle constrains distribution of tissue to be long and thin, which is the only kind of tissue that will fit in the needle. The urothelial carcinomas are resected tissue. Those are transurethral resections. And so you get a lot more tissue, and the distribution of tissue is not so uniform. So you might expect, because the slides look different, because the distribution of tissues is different slide to slide or patient to patient, that would be a harder machine learning task than prostate. And it is. One of the simple tests we did was machine learning on one slide, the left side versus the right side. It's the same patient, it's the same protocol for staining. The tissue itself isn't overlapping, and that's a start. Of course, it's much better to train on one slide, for instance, tissue and test on another, or train on one tissue and test on a different tissue. And we did that to, in terms of area under curve, the bladder, we see it's about 0.8 area under curve from one patient to another. And in prostate, it's about 0.95 or so. In terms of accuracy, the bladder cancer is cross-patient, not as accurate as prostate. Bladder cancer is about 68% accurate, which is not strong at all. It's actually pretty weak. And prostate cancer is about 95% accurate. And moreover, the prostate cancer model is about 75% accurate when predicting saliency in bladder cancer. So that was a very small pilot study. I was training end-to-end a pipeline for saliency prediction. It was minimally intrusive to existing clinical workflows in the sense that pathologists weren't changing their work. It was actually logistically complicated to collect those data with arranging meetings and the 3D printing and me being there to hold the mount, getting the proper slides scanned. So there were some logistical challenges with that. But prostate, we found, outperformed bladder. We could, in separate work, use this for other supervised learning tasks. But it was really a start for us. And I just wanted to share this because it helps motivate the second part of the talk, which is, if this is logistically complicated to do with taking videos and so on, is there a way we could scale this up and get regions of interest from pathologists, ideally worldwide, and they could tell us what's important in the slide and what's not. And so that's what I'd like to talk about now. So this brings us to the Pathobot project, which we were talking about very early in the talk. And this is a project on social media. The QR code here will take you to twitter.com/Pathobot if you'd like to learn more about this. So it is a machine learning driven pathology case search service on Twitter. It searches Twitter and PubMed cases. And published this in Modern Pathology. It's a large-ish study across many different countries and many pathologists. The QR code will take you to our published work there. And I'd like to describe to you what these cases are like on social media. So Dr. Olawuke Folaranmi in Nigeria is sharing this case of disseminated varicella or drug-induced toxic epidermal necrolysis. That's actually the question, which diagnosis is the correct one for this patient. You can see the nuclei here, just like you'd see in a whole slide image. You can see some dirty necrosis. So what's going on with this patient? He's asking colleagues on social media, and these photomicrographs are data for our project. So another trigger warning, there's a very sick patient on the next slide. If you're sensitive about that, you may want to look away for a moment. So here we go. So this is a 20-year-old, my read on this case. This is a 20-year-old mother who's taking care of her child. Her child has chickenpox. She's been exposed to that chickenpox or varicella. She's also taken amoxicillin the day before. She has blisters, you can see. And the question is, why does she have those blisters? Why is she so sick? Is she sick because she has a varicella infection, or is it because from her child, or is this a reaction to amoxicillin? And that's the toxic epidermal necrolysis. So he's asking his colleagues on social media. So Dr. Gardner in the United States responds that in his opinion, by the appearance of the blisters, this is probably a varicella infection, but to know for sure, one might take a pen like this, or a pencil, like what I'm showing here, and put that pen or pencil against the patient's skin and twist. And so then if the patient's skin breaks from that twist, then Nikolsky sign is positive for skin breaking. The skin won't break in varicella infections, but will break when the dermis is more thoroughly broken down in toxic epidermal necrolysis. So I believe in this case, the patient was negative for Nikolsky sign. Diagnosis was varicella infection. So these opinions on social media are actually really important. They've been studied in other literature. Nix et al. Have found that pathologists in developing countries like India, Brazil, and Pakistan frequently use social media, and 20% of posts they analyzed involved asking for opinions on diagnosis. So it's actually really important. So important that the United Nations has these sustainable development goals, and number 3 on that list is health for good health and well-being. And so it's good for you, of course, if you're a patient and you have easy access to physicians. That's also good for you if your physicians have easy access to each other. And social media is one way to give physicians access to each other. And we hope to make it even easier with tools like Pathobot to automatically rope in, so to speak, pathologists who have had similar patient cases. We see a wide variety of photos shared on social media. There's pap smears, there's periodic acid Schiff stains, there's hemotoxin stains, there's trichrome, stiff quicks, Yemza stains, immunohistochemistry, Congo red, fish. There's vacation pictures, there's CT scans, there's x-rays, there's all kinds of things. There's all kinds of tissues, from bone and soft tissue to breast, gastrointestinal, neurological, pulmonary. There's quite an array. There's also quite an array of different types of diseases. So herpes infections, colitis, you might see benign types of tumors as well, hamartomas and myeliomas, as well as invasive malignancies like breast cancer, gastric adenocarcinomas there. So it's quite a broad collection of data that we see. And that's good. Often in machine learning, we want very diverse collections of data for measuring generalizability. So another example of a case shared in social media is our collaborator, Dr. Ho in Belgium. He's sharing an ileal resection. This is a gross photograph and some HME sections here. He says, when hashtag breast path meets hashtag GI path, hashtag pathology, guess the story. And there's another pathologist who chimes in with it being metastatic lobular carcinoma of the ileum. And in response, she could say, thumbs up emoji, yes. So we have text annotations too, and that helps us determine what the ground truth of the image is, what kind of disease it is, what kind of tissue it is. So we use that information as well. And we have a number of tasks that we set out to perform in this work, from predicting, is an image hemotoxin stained? Is it a photomicrograph, or is it something else, like a vacation photo? You'd imagine it's a pretty easy task, but it's also really important because you don't want to make a prediction of cancer on a vacation picture. Is an image hematoxylin eosin stained, or is it immunohistochemistry? So there are two very different types of stains, two different types of purposes, so we can distinguish those as well. There's tissue type prediction. So what kind of tissue is it? Is it dermatological? Is it gastrointestinal? Is it gynecological? Is it pulmonary? Is it genitourinary? What is it? And finally, we make disease state predictions, which also powers our social media search. So we divide the universe of disease into three categories: non-neoplastic disease, normal tissue, infectious disease is the first category. The second category is benign tumors or low-grade tumors that have malignant potential, but are, for instance, well circumscribed and well contained. They're not invasive yet. And then the third is invasive cancer. It's malignant. And the QR code can take you to our work. So we iterated quite a bit in this work. So we have this cycle that Pathobot uses to acquire data. Acquiring data is often a challenge in supervised learning settings like ours. So we first start with recruiting pathologists and we ask them if they share data with us. If they consent, we download their data, we annotate the data, we train a machine learning classifier for disease state prediction on those data. So then when a pathologist searches through our bot, Pathobot on social media, that the machine learning classifier can calculate similarity. So how similar are some of the cases in our database of cases to whatever the pathologist is sharing at that time on social media. So our social media case search here is depicted first, and Pathobot responds to the pathologist with a ranked list of putatively most similar cases, and that ranking function notifies pathologists that have those other putatively similar cases that someone's linking to their case, that there's potentially a similar case out there, and it's perhaps good or worthwhile to engage that tweet and discuss. So we're trying to bring pathologists together. So one pathologist shares the case, other pathologists with similar cases are notified. We want to increase access to physicians worldwide. That's how we do it. We also search PubMed. And if you recall, we have an H&E versus anything else predictor, and we use that to filter PubMed for only literature that has H&E figures in it. So we're searching only the H&E figures in PubMed, and also provide a ranked list of similar literature in case they'd like to read some literature on potentially similar cases. And finally, we Pathobot provides a reply to itself with per disease state predictions, like how non-neoplastic this case looks, how low grade it looks, or how malignant it looks. And so this is an important sanity check. So if these predictions are wrong, then the pathologist can infer that the search is probably wrong too. So if the case is non-neoplastic, but the prediction is malignant, that would be wrong. So Pathobot and machine learning are not properly interpreting the morphology of the case. In the last step, pathologists on social media will provide their opinions, respond to Pathobot, respond to other pathologists. And sometimes they see Pathobot in action and they're inspired to collaborate with us, which loops us back to recruitment. So Pathobot just running serves as a recruitment tool for us so we can further scale up our data set and then do better because we have more data and we improve the size of the database, so search is better. So that's the cycle of Pathobot. This is Pathobot in action again, just to show more concretely a pathologist sharing this pulmonary pathology, female in her 70s, pleural lesions. She's asking for a diagnosis, giving some descriptors of morphology, and then activating Pathobot by saying @Pathobot. Pathobot also appreciates the emojis. So Pathobot responds with this ranked list of similar patient cases, and you can see a visual summary there. If you click that on Twitter, you see the full visual summary. This is just a small depiction of that. All these links go to those similar patient cases. It's similar. Pathobot responds to itself again for the PubMed search. You get this visual summary of what the article was and that particular H&E figure and that literature, and you can click to go to that literature. And then finally, there's the overall summary and per Z state predictions for each photomicrograph, and all those predictions are synthesized together for an overall prediction for the patient. So that's more concretely how. There's a question in the chat or question.
Yeah, that's me, if that's okay. So yeah, I just wanted to hear a bit more about, and forgive me if you were going to come onto this in the future slides, but of course, in pathology, there's potentially a huge amount of variation already. And often in computational pathology, we might, for example, select a given resolution, we might do some pre-processing and so on. So of course, I'm guessing that the images coming through via Twitter and even probably in PubMed, there's going to be probably more noise and maybe multiple variations of the resolution. So do you do anything to solve that, or do you just take it all in and then just try and learn on whatever's there?
Yeah, that's a great question. It's a challenge because, like you say, we don't know what magnification is. This could be 20x, it could be 10x. So one way we get around that is also there's differences in staining. So we do white balance correction. So sometimes the photo at the microscope, if you imagine like this is a microscope and you have a 3D printed mount, you have that smartphone on it. If things aren't quite aligned, there's much less light coming into the smartphone. And so then the image looks dark, it might look brown. And so white balance correction can recover that a little bit. But it's not perfect, and it's not stain normalization. So we just do a simple white balance correction, which is what other pathologists we found in our experience do when they share photomicrographs. So we just did the same thing. And the other way we try to get around the magnification problem is some of our hand engineered features. You'll see that on the right here of the 2412. Some of those features are scale invariant. So a scale invariant feature will be approximately the same for some value of approximate, regardless of the magnification of the scale. Okay. So that's how we try to have scale invariant features.
Okay, cool. And maybe just a follow on from that. I'm guessing there's going to be, especially in Twitter and maybe in PubMed as well, you might have captions in the image, or you might have some writing on the image. How would you deal with that?
Yeah, so there's a conference paper we have out that I should have included some of those figures here, where we learn a type of attention to crop that out.
Okay.
For this paper, we didn't do that. We just took a patched up version of these images and shoved it through the deep learning and calculated the features and saw what we saw. And there's some clustering I'll show later where we wanted to be sure that we weren't learning the wrong thing. So one way to learn the wrong thing is if you have a pathologist that always shares malignancy and they always sign their images the same way, or they always have the same JPEG artifacts, the machine learning might learn those JPEG artifacts predict malignancy, but they don't, or that signature predicts malignancy, but it doesn't. And so if there's a lot of enrichment or a lot of clustering per pathologist, that could potentially be a bad sign, right? So pathologists shouldn't cluster and be distinct from each other. What should be distinct is the diseases. We should see malignancy over here, low grade over here. We shouldn't see pathologist A over here, pathologist B over here. Pathologists shouldn't really matter. It matters in some ways because they take different kinds of pictures. They have different specializations like pulmonary or gastrointestinal, but maybe I'll better answer that question with those figures. But yeah, we're not, in this paper, we're not cropping out non-caption data. We're not cropping out signatures. We presented the attention work that does that at Pathology Visions recently. But it is really important. We can also crop out the black region that's outside the field of view of the microscope because there's no information there.
Great. And so we have a question online from Tilak as well. And he's asked, are there any ethical issues using social media post images and potentially patient information?
There absolutely are. Yeah, that's a great question. So a funny story. We had to make up a statement to the United States Department of State because this is an international endeavor, and they wanted to be sure that we were protecting patient privacy, for instance, of patients that were with our collaborators in Pakistan or Nigeria, because then it's a matter of state if you're not protecting patient information across national borders. So we wrote up a statement for them. And so it's vitally important to anonymize these cases, to de-identify those cases. So we needed to be sure from all the pathologists that were participating, for instance, in our disease state prediction paths, that those cases were de-identified. So we could prove to the Department of State that that was the case. But yeah, it's really important. So pathologists have developed some guidelines for themselves to help de-identify these cases on social media. So typically there's a waiting period for sharing cases. So typically one would wait, months to years and not share fresh patient cases where you might know if like your relative went to the hospital at a particular time and that case was just shared on social media. You might be able to guess who that is. And so on social media, also you wouldn't provide names, you wouldn't provide addresses, you wouldn't provide like the date they were seen, their specific age. You try to provide as little information as you can. And it's also worth bearing in mind that this is not genomic data. So genomic data can be very identifying. Sections of tissue like this are not like a fingerprint. A fingerprint is identifying, but a section of the lung isn't unique enough among patients to uniquely identify a patient. So yes, it is. There's also an ethical issue. I hope I'm not over answering, but it's a really important question. So there's also ethical issues. So in different cultures, in different countries, there are different norms. So in some countries, particularly with pediatric pathology, it's considered good practice to share the case. So you might see like a fetus and some sections of a fetus, and you'll see them on social media for a while, but then after a while, that case is deleted from social media. And it's part of a notion of respect for the dead. So you allow that case to be used for learning for a time, but then you let the case rest. You let the patient rest, so to speak. And so then those cases are deleted. And so that I feel I need to be sensitive to norms like that, because I don't want to force a pathologist to share anything more than what they would want shared or what the patient's family would want shared and so on. So there's a big like respect issue, not just like protecting people, but also respecting people. So that's the ethical side. And then how do you determine?
Yeah, please go ahead.
Okay. There's also a, so for determining the ground truth, so there's a lengthy algorithm that we have that interprets the hashtags and text. It's in the supplement of the paper of the tweets. So hashtag palm path would be pulmonary pathology. So then we would know it's lung. Or hashtag gyn path would be gynecological. Also, if someone mentions lung or mentions colon, then we know it's lung or it's gastrointestinal. So we interpret from the text what the ground truth is. And this also tells us the disease state. So they may say adenocarcinoma, so we know it's malignant, or they may say herpes, and so then we know it's infectious or non-neoplastic. We also consider the replies to the tweets, because that whole conversation is context. And sometimes some pathologists will have one opinion, some pathologists will have a separate opinion, and that's perfectly reasonable. There's room for professional judgment differences. And so in that case, we take a majority vote. And sometimes, that's not always the case. We also have annotation tools where pathologists can follow up with us individually, or if we know for sure that even though the majority opinion was incorrect because it was a super challenging case, if we know from the pathologist that has the case that for sure, like consensus conference or other means, that it was something else that's not the majority, we do the best we can to annotate accordingly. So we do have some overrides.
Great. So I think we can continue with the talk, and then if we have time, we'll come back to the next question.
Okay. Thanks for keeping us on task.
Perfect.
So
Thank
I
you.
have about 18 more minutes, so I will be brisk. So we have an original image here on the left that's patched up into 224 by 224 pixel images. This gets run through a ResNet. It's a very popular framework, very popular backbone. ResNet 50 here, it calculates at the top 2048 features. For us, that was pre-trained at ImageNet, and then we retrain it end-to-end on these photomicrographs. We also include these 10 tissue covariates for different tissue types like pulmonary, gynecological, and so on. And then there's some neuron layers on top with some dropout, and then we predict what disease state we have. For set learning, we follow what's called the deep sets approach. We take a number of these different patches, we run each through the ResNet, then we take a vector sum of all those representations, and we feed that to a random forest that does learning again on top. And that random forest has access to other features, like I mentioned earlier, the hand-engineered features for local binary patterns, fog features, color histograms, some scale invariant features that are pyramid-based local binary patterns. The random forest also has access to this covariate for whether or not some immunohistochemistry stain was requested for the case. And then we do the prediction on top. So that's like two-stage learning. I'm describing here the different features that we use. The random forest provides us a measure of feature importance and interpretability. So random forest feature importance can rank for us what features are important and what features are not important. And if you randomly shuffle a very important feature for a particular task, then accuracy will drop. But if you randomly shuffle an unimportant feature, that won't really meaningfully impact accuracy at all for the random forest. So by decreasing accuracy, we can measure importance. So before our pipeline is trained on histopathology, it's just pre-trained on ImageNet, it's just the hand-engineered features and the covariates. We measure random forest feature importance across these different features. The tissue type covariate is really, really important, more important than pretty much anything else. And that's because the incidence of infections or cancer, malignancy is different in different tissue types. So in pulmonary, it's much more likely that you'd have a respiratory infection than you would have an infection in your brain, in neurological pathology, neuropath. So it's telling us that. You can read it off a table. In contrast, after histopathology photomicrograph training, we see tissue type is less important than it used to be. It's still important, but now the deep learning features are increasingly important. If you look at the x-axis here, or yeah, it's decreasing accuracy more, so it's more important. And we see local binary patterns, texture features are quite important. So this tells us a few things. This tells us that the deep learning is learning to represent tissue, perhaps in some way when it's learning. It's also learning to represent perhaps hand-engineered features for color, for shape, and so on, but not for texture. Texture is a separate sort of thing where the hand-engineered features are still able to provide some additional information for disease prediction. So you can read that off the table and interpret what your machine learning is learning this way. Our method also localizes different disease states in a photomicrograph. So you can see, I'll be very brief here, there's a heat map for malignancy, and there's ice cold blue throughout, so there's no predicted evidence of malignancy. In contrast, this low grade or benign class, there's more heat in the center, that's yellow, and the non-tumor, non-neoplastic or normal morphology is around the periphery, which is normal tissue. So we can see some localization here, and I'll skip over those heat maps for more tissues and more patient cases just for time. We were talking about clustering a little bit earlier. Again, just to be brief, we can see in these UMAP clusters some clustering for malignancy, After we've taught our deep learning system about these photomicrographs, there's some enrichment locally for low-grade disease and some local enrichment for non-tumor. There wasn't such clustering in the purely ImageNet trained features, and there wasn't such disease state clustering for the hand-engineered features. So only our features that learned from photomicrographs could partition the space, so to speak, by disease state. And just for time, I'll keep moving forward. So just to give some empirical results for the H&E versus everything else task, it could be a vacation photo, it could be diff quick stain, which is pretty H&E looking. Error under curve there is 0.97 or 0.95. It's relatively high. It's a pretty easy task, depending on if you're leaving one pathologist out for your experimental design or if you're doing tenfold cross-validation. For the task of is an image chemotoxin eosin stained or immunohistochemistry, performance is also relatively strong at 0.99 or 0.99. And this may be useful if you had a slide archive and you knew you had slides that were H&E or IHC, you didn't know which you could partition your slides using a simple predictor like this. It's, again, a relatively easy task. More challenging tasks are tissue type prediction. What kind of tissue you have? Do you have bone and soft tissue, head and neck, logical, pulmonary, and so on? So if you take the average over all these error under curves and you weight that by how many examples we have in each tissue, it's a little bit above 0.8. So it's good enough, I guess, for research. Disease state is about the same, 0.8. You can see, different plots for error under curve for each disease state. And I'm showing you histograms too of how much disease there is per tissue. And there again, you just see more non-tumor or infectious disease in tissues like gastrointestinal. You may have an E. coli infection, gut or salmonella. Or in pulmonary, you might have a respiratory infection, some sort of pneumonia. But in other tissues, there's much less of infectious disease present, like hematological or neurological or breast. Just keep moving for sake of time. We found, well, these are area curves. So the best method we found empirically was an ensemble that used hand-engineered features, histology-trained deep features, and the tissue type covariate, and that allowed us to reach 0.8 error under curve. And we just break that down. If you just use hand-engineered features, your error under curve is worse at 0.68. As you include different covariates, you do better. As you include deep features, you do better. Ensembles do the best. We also measured performance for search. This is precision at K, so what fraction of the top search hits are the tissue of interest or the disease state of interest. We didn't optimize strongly for tissue-based search. On Twitter for Pathobot, we used disease state search instead. So the tissue type search is only shallow learning. There's no deep learning here at all. It does better than chance permutation test, but the random forest itself on hand-engineered features isn't able to do appreciably better than just taking an L1 norm over the hand-engineered features. So it is it's probably the case that the random forest can't find nonlinear combinations of those hand-engineered features that appreciably improve search for similar tissues. But for disease state, we tuned hard with deep learning. We also used ImageNet features, SIFT features, and the best we could achieve was a combination of all those things, which is interesting. You know more if you have features from different databases or for different tasks. And there the precision at K for the top hits, something like 77% accurate. Like your top hit will be the disease state in a search query. The search query will match the top hit. But as you include more hits, of course, then you have more room for including malignancy, if you're searching for malignancy, for instance. So there's a pretty good chance in 8 search results that you have. I guess in practice, we have at least about half of our search hits match the disease state, but it really depends on the query. and I'll keep moving in the interest of time. We also saw that performance varied per pathologist. Again, it depends on the lighting, the stain protocols to some extent, your camera, the quality of the photos. It really depends. So there's quite a bit of heterogeneity among pathologists, which is good in some sense, because by measuring performance here across all these pathologists, we're probably getting a pretty good idea of how we perform in general globally. So just to wrap that project up, our projects become this globally distributed expert system between the pathologists and the tools to facilitate diagnosis and bring expertise to underserved regions. It's the first pan-tissue, pan-disease method for prediction search on social media, and it's the first, to our knowledge, prospectively tested in public. We also expect our project to better connect pathologists and potentially improve patient care worldwide in line with some United Nations Sustainable Development Goals. So just with the few minutes I have left, which is good, I only really need a few minutes. We sought to maybe encourage pathologists to share photomicrographs on social media if they weren't already. We'd like to bring more people to the crowdsource, or to the party, so to speak. And we also wanted to make a better 3D printed design than we had for DeepScope. So we wanted to do better than this, me holding this on a microscope. And so we came up with something like this, which is this Pathobox thing, which can hold a smartphone. We talk about that a bit at length at this article. You can read that with the QR code at the bottom. This was published in the Pathologist. It's a nice press piece, I think. This was inspired by COVID-19 because a lot of pathologists all of a sudden started practicing telepathology at home. Many people work from home, so I thought it would be a service to the community to make a 3D printed mounting system for any smartphone or compact flash camera or even an iPad, any imaging device, and put that on the eyepiece to share photomicrographs or have a Zoom meeting, do a teleconsult, or take videos, whatever you like. Just get that camera on the microscope and share with your colleagues and get some opinions and stay connected. If you'd like to ask for a free Pathobox, you're welcome to follow that QR code and reply to us on social media. And so these different pathologists use Pathobot in different ways. In this case, Dr. Minkowitz has used it for working from home. And it's a good way to ask quick questions he finds. Just take that photo and ask some quick questions. Dr. Reese in Saskatchewan, Canada, finds it helpful for training and working with her residents, Zooming with them. She shows her setup here with her smartphone, her monitor, and her laptop all connected together here. I think that's great. Again, she started using it when COVID struck. And we've reached out to some colleagues in Nigeria. We'd like to reach out to more and more countries, of course. Dr. Ora is expecting to, I've seen he shared more on social media, more photomicrographs. He finds it useful for sharing. The tricky case for us was this Leica microscope from our colleague, Dr. Suleiman in Nigeria. Because the microscope's eyepiece is so large, it was difficult to fit our Pathobox over that. So we actually had to redesign Pathobox to accommodate that larger eyepiece. And just this past week, it fit. So that was a bit of a success for us. You can see him putting his smartphone on his microscope in Nigeria in his practice. And it's nice that works. And he shared yesterday that he could get that working. So I thought I'd share some news from us. And I think this will help with maybe DeepScope oriented projects in the future and just involve more pathologists in our project online. Here's Dr. Grisham from Toronto talking about using it for informal consultation too. So everyone is welcome to contact me if you'd like to participate in our project, get a Pathobox of your own, and connect with your colleagues. It's free. I give these away for free. It costs me about a cup of coffee to manufacture, so it's relatively cheap. So far, it's universal. It fits every smartphone and microscope we've tested over the past couple of years. And I like to think it helps engage low resource settings and colleagues on social media. So in summary, we're interested in what's important in the slide. So our pilot study in Deep Scope was to measure it. We video recorded pathologists, and presumably long looks or long dwell time, those were more important regions than regions that weren't looked at all or looked at for a very short time. It was complicated to collect those data. And I think part of the value of Pathobox is that it's now user-friendly enough that clinicians can use these mounting systems for themselves and collect data, of course, for themselves. And on social media, they can share photomicrographs themselves and get value from sharing immediately from peers and tools quickly. And that's something that actually scales up. And that's something that we found is scale enough to do machine learning on a variety of tasks. We've developed a patient case search tool to serve pathologists in the community. Personally very grateful to all my collaborators for participating in this great team endeavor on an international scale. Grateful to you all, and thank you very much. And thank you, Simon and the group, for inviting me here. I couldn't be happier to share our project. Thanks for your questions.
Great, thanks, Andrew. That was a brilliant presentation. I love the stuff you're doing with both Pathobot and Pathobox, especially Pathobox, giving them out for free. That's very kind of you. I'm sure people in third world countries love that. So if you have time, are we able to ask a few more questions?
Absolutely.
Yeah, perfect. So we can maybe start with Tilak's question that we didn't quite get around to earlier. He said, sometimes we may need IHC and genomic testing, but they're not available at the time of posting the images. And I think that was with regards to obtaining the ground truth. Do you have any comments on that?
Yeah, just a few comments on that. Yeah, that's perfectly reasonable. So one type of IHC that keratins might be ordered, you might have HHV8 stain that's ordered. So for our covariate, we only have information that an IHC was requested. We don't have information what the result was, if it was positive or negative. So we only have that much information. And sometimes pathologists share cases at that stage where it hasn't been resulted yet. So that's as much as we're really permitting ourselves to have. If that answers the question, it's actually a very brief answer, unfortunately. But
no, it's perfect. It's perfect. I've actually got quite a few questions, but I'm going to try and pick just a few because we're pretty much at 2 o'clock now, 3 o'clock. Sorry. So yeah, let me try and pick the ones that we can go with. So one question I have, of course, in computational pathology, we have lots of different data sets. Don't we? We have, let's say, for example, different challenge data sets. We have TCGA, so on and so forth. Mm-hmm. So you said that you train your model for Pathobot on social media images and PubMed images. Have you thought about potentially trying to integrate existing computational pathology data sets?
I would like to and apply the method to those data. That's part of the focus of my postdoc. So okay. I hope to share that with you very soon. Yeah, I think it's a crucially important question for taking a pipeline like this and translating it to whole slides, which is where the vast majority of these challenges are, and getting that to work. So I'm close, but I hope to share that soon.
Okay, amazing. So this is an active area of development, is it? So of course you're maintaining Pathobot, but you're trying to also extend the method you're using to actually classify these images, are you?
It is, and it's partially inspired by some of the attention work we do. We shared some of the attention work in Pathology Visions and abstract there, and that gets us there. So with whole slide images, you have to have a mechanism to separate the signal from the noise, so to speak, and attention can give you that. So this this method is completely attention naive. So it wouldn't work, but yeah, we hope soon in the months ahead to share something like that with you, the community.
Brilliant. So also with Pathobox, of course, you're able to acquire these images. So I remember and I'm asking this because I know you're now part of Faisal's group. I remember in the CLAM paper, there was an analysis on these images taken from a camera looking down the microscope. So are you actively working in that area as well? Was that like maybe
yes.
an area of interest for you potentially in the future?
Yeah, I think it's an interest to all of us to see how representations and learning on some of these modalities transfer to other modalities. So right, the CLAM paper was great for a number of reasons. One of its contributions was, like you said, learning on whole slides and translating that to photomicrographs. So I'd like to go both ways. And I'd like to show that soon, but just not not quite there. But I think it's a really important question, just because I think our field is both at the microscope and digital, so we really need to support both workflows. And I think perhaps we can learn different things. I think a crowdsourced data set like this gives us a great diversity of cases, but it's more limited in scale, whereas the digital workflows can be more focused at single institutions, but can give us a great deal of information for specific types of disease. So I think there's a lot of synergies there in using them both, leveraging them both.
Okay, brilliant. Maybe one last question. So all of the data that's acquired via Pathobot, you said it's aggregated into a database. Is that accessible for researchers to use for training their own models, or is that sitting on your server somewhere?
Presently, unfortunately, it is sitting. There are logistical challenges with respecting certain data be forgotten. And we've written some grants to try to help us scale these data sets up and be robust to just respect everyone's wishes to forget some data. But it's difficult, right? If you start with 100% of your data and then you can only share 70%,
yeah,
it's difficult for reproducibility. So maybe there's potential there for training on data in a way that's anonymized or black box in some sense. I'm open to collaborations here. I think it's a really important task for us, because we want to use as much data as we have. And it is still in some sense difficult to acquire these sorts of data. So if you have ideas and would like to reach out and collaborate on tasks like this for patient privacy preserving learning, I'd be happy to hear about that.
Yeah, because just like you were alluding to, I think there's a lot of value from potentially using all of the images that are available. So I know there was some work in our group. I wasn't involved in the work, but so they developed a model that leveraged all of the images available from textbooks, so similar to what you're doing with PubMed, and they showed that pre-training on these images was able to actually improve the performance of downstream tasks. So potentially using Twitter images in addition might be really useful for pre-training purposes.
Javenji Gamper's work, I think.
Yeah, exactly.
Yeah,
exactly.
That was great work. Yeah, I liked how he used captions there. Yeah, I think there's a lot of potential there. I mean, maybe it would help to use just the representations there. I mean, I ideally like to provide just the data, not representations of the data, but perhaps with just representations, we can preserve privacy. Do you think that would be fair?
Just share the representations. I mean, that could be done. But I guess then people are potentially limited with what they can do with that if they want to build their own representations from the original image.
It is very limiting. I haven't open to collaboration about how to preserve that. I think one of the, I'd like something almost like Path Lake, for something like this to restrict it. And, maybe there's room for us to collaborate on PathLink and get some of these data hosted on PathLink and have it in a safe place rather than a place that would be openly and publicly shared. I think if you'd be interested to follow up on mine, I'd be delighted to discuss something like that.
Okay, perfect. We can maybe organize another meeting in the future. That'd be fantastic. But I think with that, I think we're quite a bit over time now. So I think we can wrap up the seminar. And once again, really appreciate you joining us today here, Andrew. It's been a really exciting presentation. I'm sure I speak on behalf of everybody who joined us today and who will be watching once the video is online as well. So thank you so much and have a great day.
Thank you, Simon. Thanks, everyone.